For centuries, some of the biggest puzzles in the cosmos have just resisted our best theories. But what if the problem isn't our math? What if it's our most basic assumption about space itself? Get ready to dive into a radical new theory that says space isn't an empty void at all. It's a physical material with its own set of mechanical rules.
Our story starts with a challenge so tough it stumped even Isaac Newton, a problem so persistent it actually became known as the graveyard of mechanics. And it all begins with the planet closest to the sun, Mercury.
So here was the big issue. Newton's laws were amazing, right? But when it came to Mercury, they just didn't quite add up. See, the planet's entire orbit was slowly rotating, or precessing, at a speed his equations simply couldn't explain. Something was missing from the picture. And the error was incredibly precise. Newton's math said the drift should be 532 arcseconds every century. But when we looked through our telescopes, we saw it was moving just a little bit faster. The difference? A tiny but stubbornly persistent 43 arcseconds per century. For hundreds of years, that missing number was one of the biggest mysteries in all of physics. Now, the solution, according to this new theory, isn't to bend time or invent new forces. It's to rethink the very stage where all this action happens. This is the single bulk framework, or SBF for short. And it all starts with one simple, powerful idea. Space isn't empty. The SBF suggests that the vacuum of space is actually a physical medium, kind of like a thick fluid made of incredibly tiny grains all jammed together. If that's true, then planets aren't just floating in nothingness. They're moving through a real substance, a substance that can be stretched, twisted, and most importantly, can create drag. And hey, like any physical material, this medium should have properties we can measure. The theory boils it all down to two key numbers. You can think of them as the hardware specs for space. First, there's a constant that tells you how much an object's mass physically twists this medium. And second, there's something called the compliance tax, a tiny built-in friction of just over 0.2%, caused by the natural jitter of these cosmic rays. Okay, so that's the theory. But can this mechanical model actually solve that 300-year-old Mercury problem? Let's run what the theory calls the Mercury audit. We're going to treat this not as some abstract gravity puzzle, but as a straightforward engineering calculation. And the calculation is just beautiful in its simplicity. First, you use that SBF constant to figure out how much the sun's mass is twisting the fabric of space where Mercury is. Then you just add that tiny bit of friction, the 0.203% compliance tax that Mercury feels as it plows through this stuff. And that's it. So how does this purely mechanical prediction stack up against reality? Well, this is the moment of truth. Our observed data puts the missing drift at 43.08 arcseconds. Einstein's general relativity gets incredibly close, predicting 43.03. But the SBF's simple mechanical calculation, with its built-in friction, lands at 43.067. That is a 99.97% match to the actual observed data. And this just hammers home the core claim. That famous 43 arcsecond anomaly that took bending space-time to explain, well, it might just be cosmic drag. It's the friction of a planet moving through a thick, granular medium. The mystery isn't solved with complex tensors, but with simple mechanics. And this is the revolutionary part. It could shift cosmology from abstract physics to something more like tangible, predictable engineering. Okay, look, solving one ancient problem is one thing. That's super impressive. But can the theory handle something truly chaotic? Let's turn our attention to TRAPPIST-1, a solar system so tightly packed and weird it's been called an impossible gearbox. From a classical point of view, TRAPPIST-1 shouldn't even exist. You've got 7 planets crammed into an orbit smaller than Mercury's. They should have gone haywire and crashed into each other billions of years ago. But the SBRF sees it totally differently. It says these planets aren't just placed randomly. They're locked into stable grooves, or harmonic nodes, in the very fabric of space. And when you actually look at the data, something incredible emerges. If you map the planet's orbits against the SBF's predicted stable nodes, you don't get messy fractions. You get clean, whole numbers. Just look at how they line up. Planet B is at node 2, C is at node 3, D at 5, E at 8. They aren't just stable by luck. They seem to be snapped into a precise mathematical pattern. So what is that pattern? 2, 3, 5, 8. Does that ring a bell? It's the beginning of the Fibonacci sequence, yeah. The same mathematical pattern that you see in the efficient packing of seeds in a sunflower or the spiral of a pine cone. The theory suggests this is no coincidence. It's the universe's most efficient way to pack planets into a tight space to minimize stress on this cosmic medium. This is just amazing, right? It suggests the whole system is less like a random jumble of rocks and more like a finely tuned machine. But does this beautiful, simple pattern tell the whole story? What happens when we look at the outer planets?
And here is the twist. As we move outward, the pattern breaks. The next planet, F, isn't at node 13 like Fibonacci would predict. It's at node 12, and the error gets even bigger for the planets beyond it. Now, at first glance, this looks like a failure of the theory, but it's actually its greatest proof.
You see, the SPF actually predicts this break. It's called a jamming transition. This is the idea that the granular medium of space can go through a phase change, kind of like how water turns to ice. Its physical properties can literally change based on the pressure and twisting force from the star at the center. So what we're looking at is a tale of two systems in one. Close to the star, the lattice is under intense pressure, acting like a jammed solid. This forces the planets into that super efficient Fibonacci packing. But further out, the pressure eases up. The lattice relaxes, behaving more like a vibrating string, and the planets settle into stable, musical ratios, like 3:2 and 4:3. The fact that the rules change is the proof that we're dealing with a real physical material. This completely transforms our view of the cosmos. What we once saw as unpredictable chaos can now be understood with a predictable set of mechanical rules. We're essentially creating a brand new kind of cosmic map. For instance, take Lagrange points, those weird spots where asteroids like the Trojans tend to gather. Classically, it's a super complex balance of gravity and forces, but in the SPF view, it's way simpler. It's just a stagnation point in the flow of this granular medium. The lattice is literally flat right there, so anything that drifts in has no slope to roll down. They're just parked. A scientist reviewing this work put it perfectly. The infamous three-body problem, which has been a symbol of cosmic chaos for centuries, has effectively been turned into a lookup table. Instead of running these massive, complex simulations, you can just look at the lattice map and see where things are allowed to stick. This idea that space has a physical texture and follows mechanical rules is just profound. It solves old problems with shocking simplicity and gives us a new chart to navigate the universe. And it leaves us with one final huge question. If we've been staring at the universe for centuries without even seeing the very fabric it's made of, what else have we been missing?